Hello, this is Dr. Yamada. In this video, I'm going to explain the difference between distance and displacement and what it looks like when you plot displacement over time in one-dimensional movement. Let's begin with the explanation of the situation. The situation we're dealing with is not something like somebody moving like side to side as well as back and forth. Instead, we're just dealing with one straight movement from one location to another location. We arbitrarily define the home location is the position 0. Moving to the right is the positive direction. Moving to the left is the negative direction. And the person moves from home to his office or workplace. So that's the example we're dealing with. When we calculate the distance between the 2 points from his home to his office, the distance is a total path length. Okay, so the distance in this case is 5 miles. So when you think about this number 5 indicates the magnitude of the length traveled. When a value indicates only the magnitude, which is how much, right? It is called scalar. Now we talk about displacement. Displacement, by definition, is this. P is the position of the person, F is the final, I is initial, and this delta sign means the difference. So whenever you see any delta sign indicates subtraction of one place from another place. Okay, so by definition, displacement is the final position minus initial position. Using this formula, his final position is over here, which is his workplace, which is 5. And then the initial position is 0, which is 5 miles. There is additional piece of information you can obtain from displacement, which is the direction. When a value contains magnitude and the direction, it is called a vector. So displacement is a vector and distance is a scalar. So let's move on to the second example. So in the second example, instead of him moving from home to his workplace, he actually started from his workplace and going home. And we know the distance is 5 miles. However, when we actually plug in the numbers in the placement formula, we will see something different. Because the final position is not here, now it's here, which is we know that it's 0. And where he started was positive 5. Therefore, this is the initial point. So 0, which is the final position, minus positive 5, which is the initial position, gives you the negative 5 miles. So in this particular example, it gives you a different information between distance and displacement, although the first example gives you the exact same information. Now, you can not only understand the magnitude, but also this negative indicates he was moving from right to left. Okay, let's work on another example. In this case, he walked from home to his workplace, but he forgot something. So therefore, he returned to his home. So when we calculate the distance, the definition of distance is the total path length. Therefore, on the way to his workplace, he walked for 5 miles, and on the way back, he walked for another 5 miles. Therefore, 5 plus 5, 10 miles. However, when we actually calculate the displacement, his initial position was here, and actually ended up with here too. The final and initial position is identical. Therefore, it gives you the displacement of 0. So now I think you understand the difference between displacement and distance. We're going to move on. What it looks like, what the displacement looks like when you actually plot it over time. So in the first example where he moved from home to his workplace, he changed his location from one point to another. He walked completely straight. I give you additional scenarios. So before he actually started moving, he stayed for 10 minutes and then he covered 1 mile every 10 minutes. And each tick indicates every 10 minutes. So this is 10, 20, 30, 40. Something you might get confused about looking at the displacement is, well, we know that he moved straight. He never moved diagonally, but we actually see the diagonal line. Why is that? Let's understand the figure. Even though he actually moved completely straight from left to right, the figure, when you plot the displacement over time, it looks like that there is kind of a slope over here. So it's because for the first 10 minutes, he never moved. So therefore, this number should never go up. So therefore, the first 10 minutes, he stayed at the same position, same location. That's why you see a flat line. For the next 10 minutes, he actually moved for 1 mile. Therefore, this is the next 10 minutes. For another 10 minutes, he covered another mile. So another 10 minutes is over here, right? And another 10 minutes, he covered 1 mile. So when you actually connect these dots, in graph, it looks like a slope. However, the actual direction he moved was in just one direction. If somebody or something change his location from somewhere to another over time, you should see a slope. What happens if somebody moved to the opposite direction? And it should look like this. For the first 10 minutes, he didn't change his position. Therefore, there's a flat line. And you see a slope. This indicates he moved. However, you see the direction of the slope is the opposite when you compare this and this figure. So the direction of the slope indicates the direction of the movement. Again, what happened is not that he moved diagonally. Actual movement he did was moving completely straight. Okay, let's summarize quickly. So a flat line indicates no motion or no displacement. Okay? And secondly, when you observe something or somebody moves over time, you should see a slope. Okay? And the upward slope indicates a positive direction of movement, whereas the downward slope indicates the negative direction. We're going to talk 2 more points I want you to learn. To illustrate this, I'm going to give you additional scenarios. On the way to his workplace, he actually ran from start to his workplace. Therefore, it took only 20 minutes. After he get to his workplace, he was tired, so he rested for 10 minutes and he realized he forgot something. But he was already tired, so on the way back, it took actually 60 minutes. If you plot this scenario over time, what you see is something like this. So from one location, from his home to his office, which is 1, 2, 3, 4, 5 miles away, so office, right? It took 20 minutes. And he rested for 10 minutes. That's why you see a flat line. And on the way back, it took actually 1, 2, 3, 4, 5, 60 minutes to cover the same distance. Okay, so another important point I want you to learn about this graph of displacement over time is that the tilt or the angle of this displacement indicates how fast that person or the object actually displaced over time. Shallower the slope, slower the displacement over time. So that's the 4th point. The last point I want you to learn is a more complex situation where he actually moved from one place to another in just one direction. Okay, we're just talking about one-dimensional movement. In this scenario, let's talk about where he actually covered 1 mile in the first 1 hour, but in the next hour, he actually picked up his pace and covered 2 miles. In another hour, in the next hour, he actually covered 3 miles. So obviously, he sped up from 1 hour, the first hour, to the second hour, and to the third hour. So if you plot that, it should look like this. First hour, he covered 1 mile. The second hour, he covered 2 miles. The third hour, he covered 3 miles. So if the speed of his movement is changing constantly over time, so when we smooth this line, what we should see is a curved displacement line over time. The fifth information I want you to understand is when you see a displacement curve over time is straight, then it means he was moving at a constant speed. However, when you see a curved displacement over time, then the speed of the displacement is changing over time. In the next video, we are going to talk about the interpretation of the graphs of the velocity in one-dimensional movement.